Good afternoon, everybody, and welcome to this webinar hosted by Winrock International. My name is Jessica Chalmers. I've been working with the bioenergy team here for the past 5 years to focus on how we deliver bioenergy sustainably. Winrock is a non-profit organisation based in the United States with projects all over the world in line with its mission to empower the disadvantaged, increase economic opportunity, and sustain natural resources. The concept of sustainable bioenergy is central to that mission. The webinar is entitled, "Can we monitor the impacts of bioenergy on grasslands in the United States?" The purpose of the webinar is to exchange knowledge on the use of remote sensing or Earth observation data to identify and understand impacts of grassland conversion for bioenergy feedstocks. In most markets, including the United States and in Europe, there have been large regulatory drives to increase the use of bioenergy for different reasons: energy security, reduced fossil fuel use, and reductions in greenhouse gas emissions. And these bioenergy targets have been criticized by some who suggest the policies contribute to changes in land use patterns, including grassland conversions, which potentially increase carbon emissions from these conversions. In some cases, new problems could be created for key issues such as water, but in others, land use changes to bioenergy feedstocks could contribute to improvements in water quality. So understanding the impacts of bioenergy production on the environment is a key task for those responsible for developing bioenergy policies and programs. But monitoring and evaluation of the impacts over large geographic regions poses challenges. So we brought together some key researchers to present their experience and work on the use of remote sensing with respect to grasslands. Our geographic focus for today is the United States, but we do hope to extend the discussion internationally in the future. And we do understand that the subject of grassland identification and change analysis extends beyond bioenergy, and there are multiple complex factors that lead to conversion of grasslands. The underlying need is to strengthen the tools and strategies for grassland monitoring to mitigate such impacts. The webinar is going to run for 90 minutes. We have 3 presentations, and I'll introduce the speakers shortly. We would welcome your thoughts and feedback throughout the webinar. Our aim is to gather all of your contributions and present a short summary of those thoughts and conclusions that we'll make publicly available. Winrock's also publishing a report in the next few weeks on the study that we're presenting today, and we'll incorporate some of the feedback here. So a word on the format and structure of the webinar. The 3 speakers will present first, and time will be available at the end of each session to ask clarification questions. Given the number of participants we're expecting, we have the most efficient approach, which is to type your question in the control panel on the right-hand side of your screen. And you may direct the questions to the organizer that will be asked directly to the speakers. We'll collate and present the questions, as many as we can, in the time available. And at the end of the 3 sessions, a discussion session is planned where you'll be able to make comments and generate discussion, either by typing your question in the side panel, or if you'd prefer to make a comment in person, please raise your hand using the hand icon in the control panel, and we can unmute your microphone. But please do keep your comments brief and focused. Any comments or questions received in the discussion session or between presentations that can't be addressed during the time of the webinar will be responded to in writing and sent to all participants after the webinar. If you have any technical issues during the webinar, please do get in touch by messaging us through the panel on the right. And finally, we politely note the webinar is intended as a constructive and respectful exchange of knowledge, and we request the discussions and questions are conducted in the spirit. So to our speakers, first we have Nagendra Singh from Oak Ridge National Laboratory. His presentation will set out the challenge of grassland identification. Nagendra is a research scientist in the Geographic Information Science and Technology Group in the Computational Science and Engineering Division at Oak Ridge National Laboratory. His research interests include critical infrastructure, land use and land cover change, sustainability, and climate change impacts. Over to you, Nagendra. You should have control of the screen now and your slides.
Thank you, Jessica. Hi, everybody. This is Nagendra Singh, and I thank Winrock for organizing this webinar. I'm going to briefly talk about the challenges in mapping grassland, and we know the reason we are doing this because there's concern that bioenergy is going to impact grassland replacement. Now, the question is, what is grassland? And I'm no grassland expert. I basically extract information from satellite imagery. That's my job. So I went on the internet and I looked around what does it say, what is grassland, and these are some of the definitions which I found. And it's basically ground covered by vegetation dominated by grass. That's a very generic definition. But there are a host of definitions for grassland, and if you look, it says that the FAO had a meeting and there are 11 pages of definition for grassland. So it just tells us how various places and how various people define grassland. If I ask my 5-year-old what is grassland, he'll probably point out to the grassland in my backyard or front yard. But if you look at this slide, these are some of the grassland pictures which I collected from the web. And typically, a very broad classification is based on climate. So we have tropical grasslands, which are the savannas, and we have the temperate grassland, which are the cooler part of the world, not so much rain. And if you look at those pictures, you can see that it can mean anything. It can mean well-cultivated cropland. It can mean, coconut trees with cows grazing, or it can mean zebras trying to graze. So there's a huge variation of what is actually grassland. So that's I think our biggest challenge, to first try to understand what exactly grassland is, and it becomes more challenging if we try to do it on a satellite imagery. So some of the issues are, as I mentioned, are basically the major issues. What is the definition of grassland? And then there's the issue between cover and use, and there's a lot of intermixing of both of these for grassland. Some agencies, some people see it more as cover, some people see it more as use. And then there is a huge variation in management intensity. On one end, we have totally unmanaged grassland growing in the normal course, and on the other hand, we have something which is heavily managed, heavily irrigated, lot of fertilizers. And then there's the issue of multiple use. So we'll see that grassland is not just confined to one use. There can be multiple use for the same patch of grassland. There might be people staying there, there might be animals grazing, and it might be used for other purposes too. And then it has a host of disturbances associated with it. So it could be fire, it could be grazing, it could be plowing. So those are some of the other issues we have to understand before we define what is grassland. And then what is grassland also depends on temporal and spatial scales. So for example, a good example would be what we have here, the CRP land. So that's land which is typically put aside for conservation reasons. And if we look at that land when it's been put aside, we'll probably classify it as grassland. But once that land has been taken out from the program, then it will be classified as cropland. So we have issues like that. It depends on at the time scale we are looking at. And then we have the spatial scale. If we at how large area are we looking before we can really differentiate between various types of land use. Now, so let's look at some of the land cover definitions we have for grassland, and these are two popular global data sets. The global land cover data set, which was produced in 2000, and we have the MODIS land cover data set. And since these are land cover data sets, their definitions are strictly based on cover. And if you see, those yellow areas are basically those are basically all grassland in those data sets, and we'll see a more detailed picture. And the green areas are cropland. And then if many of you might have referenced the Raman-Kutty data, what he did, he took these two data sets and merged them together, and then using land use data from the FAO, he created his pasture land map, or the proportion of pasture land, which all of us have used at some point or the other. So this is what the Glove Cover 2006 looks like. This is from the European Union. It's based off the MERI satellite. And the point I wanted to make it, if you look at those classes, we have the cropland, and then we have a bunch of other classes, and these are probably based on the classification method, the input data used, and maybe the requirement. And if I just did a calculation, I'd get something around 1.2 million kilometers square of grassland based on this data set. If I took another data set for the same time period, and then you see that the classes are defined somewhat differently, the area of grassland kind of doubles. So here I'm not going to go into which data set is right or which data set is wrong. It's just depending on which data set you use, things will be vastly different. If we look at another data set, which is our national land cover data set, the last one, which was produced in 2006, the area of grassland is somewhat in between those two data sets. So, and we can assume that this is probably a better estimate because this is done nationally, and a lot of time and effort is put into this. So you can see that just by choosing different data sets, we can have a huge variation, and it again goes back to as to what really are we calling as grassland. Now, if you look at some of the land use definitions, so the US Census of Agriculture, they also produce every 5 years, they give us numbers for these categories. And if you see, their definitions are based more on use. And these are probably more realistic because it tells us about, it gives us much more information about the grassland types instead of just telling what type of cover it is. But the thing with this is that these data sets are usually tabular data sets, which you will get at the county level. So though they give us more information, they might not be very useful for understanding land use, spatial land use changes. So it's very difficult to understand what type of grassland was converted into what, because these data sets are not spatially explicit. So the advantage is that they give us more information. The disadvantage is that we cannot use it for doing spatial land use change. Now, this is again, I have just taken some of the major data sets and I have just plotted of what you could call as grassland. And then there might be argument that, okay, why did I use this class, or why did not I use that class? But this is just one overview of the things. And again, the point I wanted to make is that this is a very subjective interpretation of grassland. And again, it can vary depending on which classes which we choose to call grassland. Now, this is the cropland data layer. All of you must have used it at one point of time. It is probably one of the best data sets out there as far as crop mapping is concerned. And the best part of it, it is available every year. It's now available for the whole of the United States. It has an excellent interface to do some spatial analysis through the Cropscape website. You can download the whole country. You can download a part. So if you talk to people, and I haven't seen a better data set for crops than the cropland data layer. But then, can we use it to map something like grassland? And I'll just go into the reasons what could be some of the issues if we try to use something like the cropland data layer, which does a great job of mapping crops. If you look at the recent version, it probably has more than 200 classes, which I think is amazing. But so if we just look at the 2008 serial, this is a part of Montana, North Dakota, and then if we look at the 2009 data set, we see that there's a big shift. And the reason is that because this classes was not map consistently. So we'll come to the assumption there was a lot of grassland disappeared from 2008 to 2009, which probably is not the case. Similarly, if we look to another region, this is 2010, and then if you look at the right corner, like the Dakotas, you'll see the same thing happening. And it's not that a lot of grassland appear, it's probably because the thrust of the cropland data layer is to not map grassland consistently. Their thrust is more to map individual crops. So if every time we try to take these type of data sets and do some analysis for which it was not intended, then we run into troubles. This is another plot for the state of Iowa, and the reason I took it because we have data for all the way from 2001 to 2011, and if you see, it's difficult to kind of synthesize the information because classes come and go. Now, if I were to do the same thing for corn and soya, I would probably get an excellent trend of what's going on with corn, soya, or alfalfa in Iowa. But if I try to do the same thing with the various grassland layers, I'll probably not get a very convincing answer because, as you see, some of the classes come and then they disappear and then they reappear. So, and then, as I said, that depending on how I aggregate my data sets, for different areas, I'll get completely different answers. So depending on how I aggregate, I can show that grassland was replaced by cropland or cropland was replaced by grassland simply by aggregating data the way I want to aggregate. And as I said, that different agencies have different purposes of creating this data set. So it's very difficult to compare data set against each other, but we are doing that all the time. So, and if you look at, this is some of the definitions of grassland which we have in our data set. This is just a tag cloud which I created using all the definitions of grassland in various data sets. And this is again taken from a USDA report which recently talked about the impact of insurance and stuff like that on grassland. And this is from the prairie pothole region. And this is something which we would call grassland, but then if we looked another one, this is what would we call it. So we see this grassland, and then beyond that we see cropland. And it's very difficult to map these things in an imagery or to separate them out because they are so close to each other. So you can see in a given area we can have different types of grassland, and to understand what's going on overall, it becomes a challenge. So the question is, why do we have such a high variation in grassland estimates? And if you go back, the main reason is that grassland is not just one class. We cannot just call something grassland and forget about it. Grassland can mean so many things. And when grassland means so many things, it becomes a challenge to map it. So if we try, because unlike crops, grassland vegetation is rarely homogeneous unless it's been planted and managed. So each grassland type can consist of mixtures of grasses, forbs, and even shrubs. And in addition, there might be patches of bare soil which come and go, particularly in dry regions. So all these factors create an environment where getting pure pixels is a rarity and where we get considerable spectral heterogeneity within a single grassland pixel. So the uses of grassland can include grazing and haying, intensity and seasonality or timing of use. And if we try to understand all these aspects just using satellite data, it's not possible. In addition, grassland is also sometimes burned in the spring to simulate productions. So all these create a big challenge, because if you look at data, sometimes the spectral variation is simply due to the management practices and not because of the different types of grassland. So, and I'm sure if there are ways to map grassland, but right now it's a big challenge to differentiate grassland using satellite data. But the reason here we are is not because we are interested in the types of grassland. I think the bigger question here we want to answer is land use change. And what we think is that we first need to understand what is land, what is the use, and what do we define as change. And we need to understand the representation of various policies in various models. And we need to have a framework to understand the drivers of initial changes in land use and land cover and understand the causal relationships between them. We need to understand the constraints. We need to understand what is our land supply, our productivity, and our management specification. We also need to take into consideration the economic factors, the baseline choices we make, and various other factors which are very relevant in understanding land use change. Just by mapping grassland, that's not going to give us any true picture of whether, because the question I think we're trying to answer is bioenergy causing changes in grassland? And just by mapping grassland accurately, we cannot answer that question. So thank you for listening, and I'll take any questions which you might have.
Thank you very much indeed, Nagendra. We have not had any clarification questions submitted by panelists through the control panel, and I don't see any hands raised at this time by any of the panel attendees either. If anybody would like to ask a clarification question, please either raise your hand or type the question in the control panel on the right-hand side. If we don't have any questions at this time, we can move to the second presentation, and should any of you feel you need to ask a question during the presentation, we can address questions for both presentations at the end of the second one. So I don't see any more questions, so let's move to the second presentation. Our second speaker is Dr. Chris Wright. Chris Wright will present his recent work on the US cropland data layer to identify grassland-cropland relationships. Dr. Wright is a landscape ecologist with research interests in wetland ecology, environmental trends, amongst other things, and he has worked largely in wetland and grassland systems, mostly focused in North America and Central Asia. Before joining South Dakota State, he was a National Research Council postdoc associate at the U.S. Geological Survey Center for Earth Resource Observation and Science. Over to you, Chris. You should now have control of the slides.
Great. Thank you very much. So, guess I'm still, oh, there we go. Okay, so Nagendra just presented a case for why we shouldn't be able to draw any conclusions from existing data sets. And that's all very nice and good, but the problem is that the land cover change that we're seeing in this part of the world is occurring so rapidly that there really isn't time to do some of the analyses that he's suggesting, and basically what we need to do is make the best use of the data available. And I would argue that really this isn't all that difficult, and we don't need to go into nearly such detail. So, excuse me, whoops. My co-author and I had a paper in PNAS that I think many of you are aware of, and Nagendra and I have had exchanged letters over that paper subsequently. And we were pretty amazed by the response in the media. It was much more than we expected, but you know, there were pieces at NPR, Guardian of London, when they're not going after the NSA, talked about the biofuel belt creeping across the U.S. And then there was interest in some areas that we wouldn't have necessarily expected, particularly in the hunting and conservation communities. So there's a broad interest in this issue in our part of the country, mainly because people see what's going on in their everyday lives. And then of course there was pushback from the biofuel industry, and here's a quote from the Renewable Fuels Association: "Results are highly questionable and are irrelevant to the biofuels policy debate." So thanks for coming, and I'll move on to these irrelevant results. Okay, so whoops. As far as I see it, there's two main policy drivers of grassland conversion at the national level, and the first is the renewable fuel standard. So here you can just see the corn prices relatively stable up into the 2000s, and then when the renewable fuel standard was put into play, we have a rapid run-up in ethanol production and an increase in prices. And so here's probably a blatant misuse of statistics, but this is the corn price versus ethanol production, and certainly we shouldn't infer causation from correlation, but I think it's fair to say that without the renewable fuel standard, we wouldn't have seen the run-up in prices that we've observed. Okay, so what are some of the end uses of U.S. corn? Well, one of the arguments for the increase in price is that increased global demand for protein is driving up corn prices. And you can see on the left, the rapid run-up in the amount of corn that's gone into ethanol in the last 8 years or so. And this is up through 2009, and you can see exports are relatively stable. But if you go over to the right panel, you see these are first the leading importers of corn. There's been a steady increase in corn imports, but and this is up to 2013. But if you look at leading exporters, there's been a rapid drop in U.S. exports in the last 3 or 4 years. So my argument would be that that just doesn't hold water. That the higher prices are coming from increased demand, especially since the U.S. share of exports has really dropped precipitously. And then the second driver is subsidized crop insurance. Federal expenditures upwards of $20 billion last year. And then on the right, this is the area where we're focused: North Dakota, South Dakota, Nebraska, Minnesota, and Iowa. And you can see that the crop insurance subsidy exceeds the direct subsidy for most of the area that we're interested in. This is just a quick summary of agriculture in South Dakota. From about the 1910s through the 80s, we were primarily working with a corn-oat-hay rotation, and that was to control the corn borer. And so you needed to have oats and hay to break up the life cycle of the corn borer. With the adaptation of modern pesticides, there was no longer a need to do that rotation, and so farmers have gone into almost a straight corn and soybeans rotation. This is just the total crop acreage in South Dakota over time, and you can see a rapid decline in the 20s and 30s associated with the Dust Bowl, then a increase during World War II and in the post-war era, and then we reached this peak production around in the early 1950s. There was a lot of concern about the implications of that, and so the soil bank program was established, which retired grassland retired cropland and put it into perennial grasses, and that really drove down the total acreage. And then there's been a steady increase in crop acreage since the soil bank program up through the present, and that's despite the fact that the Conservation Reserve Program was implemented in the in the mid-'80s and continues to this day. So the upshot is, despite these major conservation programs, we're right back to where we were in terms of the historical peak, indicating that there's tremendous pressure on bringing more land into production. Okay, so USDA has been studying land cover change at least up to 2009, but primarily on the state level. And I apologize, my one-to-one line is a little bit off. But in Minnesota and Iowa, the increase in corn acreage was offset by decreases in soybean acreage, whereas in Nebraska, North Dakota, and South Dakota, we have increases in corn acreage, and then with the exception of South Dakota, decreases in soybeans. So South Dakota is leading this area in terms of increased corn production and increased soy production. Okay, now what we were interested in is in finer scale change, so not at the state level, but at a finer spatial grain. And again, in the western corn belt, which are the Dakotas, Nebraska, Minnesota, and Iowa. And the data set we used was the CDL. For 2006, we defined a generalized grassland class. So that would be grass pasture, grass hay, idle cropland, and herbaceous grassland. And what Najendra didn't mention was that, yes, there are inconsistencies in the classification scheme, but most of those inconsistencies are between these different grass classes. So, and that was something we expected when we went into this study. And we believe by doing a generalized class, you avoid some of the issues that he brought out. And then we compared that 2006 NAS to the 2011 combined corn-soy class. And so this is just a brief schematic of the overlay analysis that we did. So we go from the 2006 CDL, extract out the generalized grassland class. Then the 2011 CDL, we have our generalized corn-soy class. Then we overlay the two, so where we have an intersection, we've identified grass to corn-soy. And you can see there's quite a bit of noise in that change layer. So what we do is we use what's known as a 5x5 majority filter to filter out that noisy change, and the result is we get these objects that look like agricultural fields. Okay, so here's just the area of change summaries. Now we also looked at corn-soy to grassland as well as grassland to corn-soy. So we have 2 million acres of grassland to corn-soy, 663,000 going the other direction for a grassland net loss of 1.3 million acres. Okay, so what does this mean in terms of net carbon impact? Well, I just did a back of the envelope calculation based on Gelfand et al. Results in terms of greenhouse gas impact of converting CRP lands. And I come up with about 4 million metric tons CO2 equivalent associated with this land cover change, and that's about one coal-fired power plant for 1 year. So it's not a huge amount of carbon, but it's not a tiny amount either. And then there's the issue of, well, how do you pay back the carbon debt that you accrue through the conversion event? And Gelfand have some, ballpark figures, and the more realistic one is to go to a corn-soybean rotation, and then he has a conventional tillage versus permanent no-till, and in reality, most farmers are going to be somewhere in between. So between 30 to 90 years to pay back the carbon debt of conversion. Okay, so this is just a bunch of other processing that we do with the CDL to address some of the issues that Najendra brought up in terms of trying to extract what we believe is useful information from these data sets. And I can go into detail offline, but I just wanted to bring up the fact that we are aware of some of the difficulties in using the CDL, but we've basically tried to take as many prudent measures as we could come up with to get useful information out of these data. And that's primarily because it's the best data to work with, and we have rapid change that's occurring in our part of the world. Okay, so the next thing we did was we estimated rates of change at 560 meter spatial resolution. So on the left we have estimated rates of grassland to corn soy conversion. So this is an absolute rate, percentage of the landscape that's changing. And then on the right we have corn soy to grassland. And you can see that there's much more change in the grassland to corn soy direction than in the other direction. Okay, so next we estimated relative grassland conversion rates, and we just did that using the absolute change layer, dividing by a smooth grassland cover layer for 2006. And then we come up with the relative grassland conversion rate. And you can see that, that this is primarily concentrated in eastern South Dakota and North Dakota, in southern Iowa, down here in the hillier part of the state, and then out in the eastern driftless area in South Dakota, and then through central Minnesota. So basically you have a bathtub ring of change surrounding this core corn and soybean growing region in southern Minnesota and northern Iowa, and then a little bit of expansion as well out into Nebraska. And these rates are actually quite high in some areas. 30% over 5 years. That would be about a 5% annualized rate. Okay, so the next thing we looked at, well, what types of land is conversion occurring on? And what we did was we overlaid those change areas on the USDA land capability classification. And the way that works is it's 8 classes. 1 through 4 is arable land. 5 through 8 is generally considered non-arable lands. And then in all land capability classes, well, class 1 would be considered prime farmland. And then 2 and higher, what USDA does is they assign a modifier to that class, which basically consists of the primary impediment to production on that land. So, so this is just the total amount of change divided up by those LCC classes and then their modifiers. And so you can see that most of the change is occurring on class 2 and class 3 lands, and largely concentrated in land subject to erosion. This orange modifier, as well as a soil modifier, which indicates rocky soils or shallow soils. So here's 2 examples. This is a relatively steep hillside being tilled, and then down below we have a bunch of rocks that have been taken out of a neighboring pasture prior to it being tilled. But basically, the take-home message here is that the conversion is occurring on poor lands that are subject to erosion and/or have poor soils. Okay, now if we break it out by states, so this would be Minnesota, and you can see that most of the conversion is occurring, or a substantial amount of conversion is occurring on land subject to this wetness modifier. So that indicates lands that are either seasonally flooded or have a high water table. And the implications of that is there's been a tremendous amount of drainage tile installed in Minnesota, with impacts on runoff, erosion, etc., water erosion of stream banks, etc. And the image on the right is the Minnesota River flowing into the Mississippi, and you can see all the sediment coming out of the Minnesota River. Okay, so in Nebraska and South Dakota, we see that this climate modifier is predominant, and that just reflects the fact that the Corn Belt is moving to the west into more arid lands. And then obviously, you know, one of the concerns that arises from that is, well, what if we get severe droughts? So this is a wilted corn crop on highly erodible lands. Are we headed towards another Dust Bowl like event? And I don't think we would have another Dust Bowl just because the tillage practices are so different now. But I think there should be real concern that the Corn Belt is moving into much more arid areas. Okay, so lastly, we looked at grassland conversion in relationship to wetlands. Much of the area that we were working falls within the prairie pothole region, and here we have a landscape that's dotted with millions of these small closed basin wetlands surrounded by agricultural land uses. So you have corn production. I'm not sure what this could be, soybeans that haven't turned yet, and grassland, either pasture, haylands, or native prairie. And what we find is that a tremendous amount of grassland conversion is occurring in close proximity to those wetlands. So here in this figure over here, 80%, upwards of 80% in North Dakota and South Dakota is within 500 meters of a wetland, and more troubling perhaps, nearly 40% of grassland conversion is occurring within 100 meters of a wetland. And out in Iowa and Nebraska, there's basically very few wetlands left. Minnesota falls in between. And then down below, here's just two examples of tillage right up to the edge of a wetland, and then within a larger, up in the uplands surrounding a wetland. Okay, so why is this a problem? Well, 50% of North American ducks breed in the prairie pothole region. And so here we have an example of ducks in a prairie pothole with tillage coming up right up to the edge of the wetland. And why is that an issue? Well, ducks require grass nesting cover for predator avoidance, and the figure on the right is from Reynolds et al. And just illustrates the reduction in daily survival rates for nesting duck species as the amount of perennial cover surrounding wetlands is reduced. Okay, so just in summary, I think it's pretty clear that the Corn Belt is rapidly expanding onto less suitable land and into less suitable climates. And I'd argue that this is one of the most important land cover land use change events in recent U.S. history. And just one final point, if we waited around for better data and better analyses, I think we would not only miss observing this event, but we would neglect to do something about it. So my argument would be that yes, we can use the CDL to assess biofuel impacts on grasslands, but we do need to do it judiciously and with forethought and careful analysis. So with that, I'll take questions if there are any.
Thank you very much indeed, Chris. We do have 3 questions at the moment. I think what I shall do is some of them are quite detailed.
Okay.
So if you don't, I will ask them, each of them individually, and give you a chance to respond. So first of all, on one of your earlier slides that illustrated the into and out of corn and soy and grassland,
Yes.
one of the questions is there seems to be quite high back and forth conversion, for example in Nebraska. Is this suggestive that categorization errors are on a comparable scale to real land use change, or is there a reason to explain this back and forth conversion?
Well, you know, the issue there is we're mapping at 560 meters spatial resolution, so you could have back and forth. And historically, there has been quite a bit of back and forth in terms of moving land into pasture or hay for a number of years and then going back into corn. And that's actually been documented by USDA that, you know, up through the early 90s, there was quite a bit of movement back and forth between grassland and corn soy, and that the idea now is that rotation back and forth is not happening anymore. That people are going to corn and soy, and they're not going back. So I guess with respect to Nebraska, I would argue that that may very well be real rather than measurement error. But certainly some of that is probably measurement error, but the idea being that, you know, the change in one direction is so much more obvious than in the other direction.
Okay, thank you. And the second question is that since Nagendra explained estimating areas of grassland accurately is not possible, or at least very difficult, how accurate are the estimated changes for North Dakota, for example, with respect to grassland and soy, and the reverse that you showed in your slide? So I think this question is about the accuracy tests or statistics on the land use changes.
Well, there's no way of estimating the accuracy at this point. I mean, you can use the accuracies published by, I guess you could try and extrapolate from the CDL reported accuracies. The accuracies for corn and soybeans are actually quite high. So my argument would be that the CDL does a very good job of identifying corn and soybeans. And if it's not in corn and soybeans, it's most likely in pasture or hay.
Okay. We've got several more questions coming through, so I'll give this another few minutes because these are very relevant to this particular presentation. A question from the University of North Dakota, Rob Proul. Non-agricultural grassland classes are hardwired into the 2006 CDL using data from the 2001 National Land Cover Dataset and into the 2011 CDL using data from the 2006 National Land Cover Dataset. Did the change in these National Land Cover Datasets merit special consideration in your analysis, or did creation of an aggregated grassland category negate the impact of this change?
I would argue that the aggregated class negates the change, primarily because the CDL reverts to those classes when the analysts decide they can't identify a crop type. So one of the problems is that the pasture hay class in the CDL, or excuse me, in the NLCD, is actually both legume dominated and grass dominated land covers. So that includes alfalfa. And that's why we did not use that class. So we're using the NLCD where if we're ever using the NLCD, it's where it reverted to where it was herbaceous grassland, and we're pretty confident that that's actual grassland. So really the issue is how good is the CDL we don't include alfalfa in our analysis, and that I think caused some confusion, at least with the folks at DOE. It's very difficult to crosswalk the NLCD and the CDL because of the way that the NLCD mixes alfalfa in with grass pastures. So I don't know if that answered the question. But
well, we'll see. If there are additional questions that pop up, do panel people on the webinar welcome to send them through, and we'll perhaps do follow-up questions at the end of the 3 sessions. There are some more questions that have come through that are perhaps more general, and to those that ask the questions, we will move them to the end of the 3 sessions. There's one final question that's specific to this presentation, which is, can you explain the logic behind including the idle crop class as part of the grassland class?
Because in the area we're interested in, that idle class is typically CRP land. And actually, we don't have much bare soil fallow in our part of the world, so we were comfortable with using that idle.
Okay, thank you very much indeed, both to Chris and to those asking questions. I think we'll move now to the final presentation. And again, if there are further questions from any of you to any of the presentations, please do just use the control panel in the right-hand side, and we'll present them at the end of the session. So 2 speakers will deliver the final presentation. Kevin Brown is a GIS and remote sensing analyst with Winrock International's Ecosystem Services Unit. And Mike Netzer also works for Winrock International as a carbon analyst for land use change and climate change mitigation. He is in GIS and spatial modeling technologies. They are going to be discussing some of Winrock's recent work on the use of a spectral mixing technique to better identify aspects of grassland that will help us assess what the potential impacts of conversion to bioenergy may be. Kevin and Mike, over to you. You should have control of the screen and your slides now.
Thank you, Jess. What's that? Can you guys hear me? Yeah. Okay. Trying to change the slides now. Oh, there we go, a little bit too far. Okay, thank you. My name is Michael Netzer. Thanks for the introduction, Jess, and sitting here with me is Kevin Brown. So we looked at the interaction between biofuel crops and grasslands for a specific region. As we've kind of been talking about, or as we've been talking about, the U.S. and many countries have set targets to increase the use of renewable biofuels to reduce dependence on traditional fossil fuels, right, to reduce greenhouse gas emissions. But as we've just seen, you know, there are a lot of land use change implications that can negate those reductions in greenhouse gases if they're planted on higher biomass environments. Similarly, there can be other negative impacts from the expansion into native grasslands, as we have been talking about, right, for many of the ecosystem services that we rely on, biodiversity, habitat, water quality. In the U.S., as this webinar is focusing on, we focused on most of the change is occurring on grasslands and rangelands, and so we as well focused on that. With these potential benefits also, there are those potential negative definitions of, and so you must define what is kind of sustainable biofuel production if you are to initiate these biofuel initiatives. What is sustainable could lead to a long discussion, but in general, this study assumes sustainable development as biofuel crops that are planted on land that is lower in biomass and either not contributing significantly to the overall ecosystem services, say biodiversity, habitat, or water quality, or is degraded, say that kind of in quotes, and is considered land that currently affects ecosystem services negatively. For example, ground that is exposed ground and leads to sediment, increases in sediment load within the waterways and nitrogen and leaching. In the context of this study, as we're focusing quite a bit on the remote sensing and the ability to monitor it, we looked at even a narrower band of what is sustainability, and future studies would have to look at whether these indices of sustainability correlate with their particular study area and their questions. But in a sense, we were looking at those environments which are lower biomass, say, than the grassland, right? Which if you convert a grassland into a lower biomass crop, you actually are emitting CO2 into the atmosphere by that land use change. And as I said earlier, that can result in negating any benefit that comes from actually planting biofuel crops. And also, as far as there's also correlations with the exposed soil, right? So the amount of grass cover over a certain area. And so the reason we narrowed these two definitions down is largely for remote sensing purposes, and also because we were not able to do any kind of ground validation for this particular study. So as we've been talking about, remote sensing is a key tool for monitoring the impacts, right? As Dr. Wright was saying, what tools do we use? These tools are available, these large land cover maps. How are we to use them? And we certainly must, to some degree, try to solve these problems. So remote sensing is an excellent tool for doing that. So the topics of this study looked at 3 general questions that we can remote sensing tools and data answer this study to answer questions of remote sensing, the tools and data sets to inform, evaluate, and monitor sustainable development of biofuel. First, we asked, are the current, as we've been talking about quite a lot, are the current remote sensing products for the U.S. sustainable for measuring grassland change? And as we've talked about, the Cropland data layer is by far probably the best data set capable of doing that in the United States. So we assessed the Cropland data layer. Then we asked, can the Cropland data layer grassland class be improved to represent different grassland conditions that will inform the, quote, sustainable versus less sustainable development of biofuel crops? And last, we took a next leap at another question that has been intriguing us. With an improved grassland classification, can we get improved hydrological modeling results, i.e. ecosystem services, assessing other ecosystem services, right? So can we improve the Cropland data layer to improve monitoring of biofuels and improve our analysis of the potential impacts on water quality, one of the main ecosystem services, right? Okay. So for our study site, we selected the Fort Pierre National Grassland and some of its surrounding counties in South Dakota that you can see in the map here on the screen. We selected this site because it has experienced a decent amount of change in grassland and croplands over the last 5 to 7 years. It has a mix of grassland conditions from low sparse, what we might call sparse grassland, or low biomass grassland. These definitions are slightly fuzzy for our study only because we don't have a lot of ground data to go off of, but I digress. To more lush biomass grasslands as a result of different management and ecology in the region. It had some ground data that we were able to obtain from the Fort Pierre USDA office there. And it had a hydrological gauging station just to the east in the Cedar Creek watershed, from which we might be able to assess some changes in the hydrology. So we tried to take a stab, and this gets very closely to both of the last presenters, at doing an accuracy assessment on the cropland data layer for the grassland classes and the crop classes and the areas of change. Now, how we did this was, again, not through field work, unfortunately, but as best we could using kind of the available data sets. First, it's important to point out, as we've kind of been talking about, that the cropland data layer is developed primarily for mapping croplands, and that only the cropland classes are adequately assessed for accuracy and calibrated, and only those classes are calibrated based on ground locations. As we've also talked about, the non-cropland classes, forests and grasslands, are derived from the National Land Cover data set, another remote sensing product. Therefore, it's not actually derived from ground data. This is the training data, right, which is used to train and inform the development of the cropland data layer. Also, the National Land Cover data set was the most recent one, as we've been talking about, was produced in 2006. This does limit the relevance of the current cropland data layer's ability to assess the accuracy for non-cropland classes. I believe that the cropland data layer simply cites the last National Land Cover data set as the accuracy for pretty much all non-cropland classes. But as Dr. Wright said, that's not the focus of the cropland data layer. Nevertheless, if we're going to use it for analysis of grasslands, it's important that we understand the errors and accuracies, as we've all been talking about. So to assess the cropland data layer as a tool for monitoring crop expansion into grasslands, an accuracy assessment was conducted on areas of grassland and cropland between the time periods of 2006, the cropland data layer for 2006, and the cropland data layer for 2010. 120 locations were placed, 50% in areas that were classified as crop and the persistence of crop and grassland. You can see in the map to the right, persistence of crops is in brown and persistence of grasslands is in green. That meant no change occurred between those two time periods. And then 50% in areas of change, from grass to crops and from crops to grass. It's important to note that the 50-50 distribution skews this accuracy assessment toward areas of change. Areas of change were only about 12% of the study area, so this undoubtedly affects the overall accuracy, most likely, undoubtedly reducing the accuracy, because areas of change are just inevitably more subject to error than areas of persistence. So these areas were assessed not by going to the ground, but by placing them over Google Earth's high-resolution imagery. Those plots that could not be assessed in the imagery were tossed out, and so we made our best attempt to validate. The general results that were for both the 2006 and 2010, accuracy was right around 80% for the cropland data layer, for the study area only. This isn't for the whole cropland data layer, of course. And as well, as I said, these results are slightly skewed, probably towards lower accuracy due to 50% being in areas of change. The error matrix, if we only assess areas of persistence, it's much higher. The accuracy is 94%. In contrast, if we only assess areas of change, the error accuracy is much lower at 71%. The error matrix shows that for errors for grasslands, the accuracy is consistently lower, 3 to 15% lower. In general, it's hard to say, right, what is a good enough accuracy for a remote sensing layer, or what layer should be used for monitoring. more importantly, for making policy decisions, right? However, there are examples of other remote sensing products and other arenas of study that have suggested standards of around 80% accuracies, considered good enough. The Cropland greater than 80%. The Cropland data generally reports greater than 90% accuracies for many of the dominant crops, corn, soybean, yes, the dominant crops. So that is kind of the target I see for the Cropland data layer. Our general conclusions from it, this study for this small area, is that yes, the Cropland data layer is doing a good job of mapping these different areas. It certainly could do a better job if it put the same effort into grassland classes as it does in cropland classes, maybe by actually validating based on ground data and a number of other things. However, we're not here to make recommendations to those developing the cropland data layer. And the second conclusion is that the classification of grasslands is wholly inadequate in the cropland data layer, the different classes within grasslands, and therefore there necessitates quite a need to, if you are to monitor biofuels, to drill into different classes from, say, lush to sparse. And on that note, I will hand it over to my esteemed colleague to talk about potential areas and ways to do that.
Thank you, Mike. Hello, everyone. This is Kevin Brown. And so, as Mike just mentioned, the CDL is a useful tool with some caveats for identifying the location of conversion of grasslands. And such a map is useful because it allows us to ask some broader environmental questions about the impacts of biofuels expansion. And one of those questions regards not just whether something is a grassland or not, but the conditions of that land which is being converted. And as we know, the CDL does provide several different grassland classes, but there are issues with consistencies over years, definitions, and over large areas, all grasslands are simply grouped into one homogeneous class. As you can see in this comparison between the CDL and Google Earth imagery, there's a lot of variation that's being lost in the CDL. So one of the goals of the study was to see if those more broad CDL categories could be further refined by some measure related to the ecological value of the natural land cover. So the question was whether grassland conditions could be adequately measured remotely, at low cost, and repeatedly. And this is clearly where the availability of free and high-quality Landsat imagery makes remote sensing a very attractive option. The problem is that traditional vegetation indices, such as NDVI, perform poorly in grasslands, or they require very high data standards. Images have to be from the peak of the growing season, or they require a time series of multiple images. A primary issue with NDVI is that it cannot readily distinguish between senescent or dry vegetation and bare soil. Even the most ecologically valuable grasslands will obviously go through periods of senescence when they'll appear brown and can be easily confused with bare soil in a more traditional band ratio index. So this is really the advantage of spectral mixture analysis, which is what we use in this study. By defining the spectral signature for each of 3 pure material classes, technically referred to as end members, for bare soil, green vegetation, GV, and non-photosynthetic vegetation, NPV, spectral mixture analysis can estimate the % of each pixel that is covered by each of these materials. The higher percentage of the surface covered by GV and NPV, or green and senescent grass, the higher the ecological value assumed in this study. The image that you're looking at now in this slide is of a visualization of some SMA output covering the Fort Pierre National Grasslands in South Dakota. Areas which are most strongly skewed towards GV and soil, which you see as red and bright green on your screen, are areas associated with agricultural activity outside of the study site. But within the study site, you can see that even though the gradients are a little bit more subdued, it's possible to discern the outlines of various pasture plots that have received different management treatments over time. So SMA can be quite sensitive to small variations on the ground. So the index that we use as a proxy for the ecological value of grasslands was the sum of the GV and NPV end members, or material types that was output from the SMA analysis. And this image here shows the degree of detail that can be gained by this analysis. The Landsat scene in this SMA output was taken from September, at a time when grasslands exhibited a mix of both green and senescent vegetation. SMA was able to identify vegetated areas, green or otherwise, as distinct from bare soil. You can see in the high-resolution Google Earth imagery that the most pronounced soil signature occurs along the slopes of exposed bluffs and heavily eroded areas, the areas that you see in red on the lower right. And of course, anyone considering using spectral mixture analysis will want to know how these remote sensing derived measurements would really line up with ecological variables that are relevant to biofuel policy. To that end, we attempted to find statistically significant relationships between the GV and NPV values and two data sets recorded by the U.S. Forest Service from Fort Pierre National Grasslands. The first variable was a grass height value recorded along 100-meter transects, and the second conveys the number of years that a pasture unit has been allowed to rest. Ideally, we had hoped to demonstrate that both taller grass and longer rest periods would show a positive relationship with the GV and NPV values. We were unfortunately able to do so. Some issues we faced were that we did not have control over the selection of these explanatory variables or the collection of the field data, and thus we were forced to make some suboptimal assumptions in our study. But in a more robust study with more resources, it would have been preferable to go and collect our own field measurements. Overall, though, in our experience, using SMA is very easy to implement, and just by visually interpreting the output, the maps that it outputs, it was able to convey more information than an index such as NDVI. And that's really where we come to one of our conclusions of SMA, are that any monitoring program considering using SMA needs to invest considerable upfront effort into the initial calibration of the spectral signatures used to define bare soil, non-photosynthetic vegetation. Because all of the values resulting from SMA are calculated exclusively from these signatures, the final results are sensitive to their initial definitions. Furthermore, differences in regional mineral soils and prevailing vegetation assemblages mean that signatures need to be defined separately for different regions. So it's a very labor-intensive task up front. But once this has been established, it doesn't necessarily need to be repeated. The spectral signatures that are recorded should be valid for that region as long as that sensor for which that signature is to be used, Landsat 8, for example, continues to be operational. And that statement also applies to the establishment of relationships between green vegetation, NPV, output of SMA, and a variable of interest such as biomass. That's really what the policymakers want to know in the end, is something that has ecological relevance. So those relationships also need to be established independently for different grassland species assemblages. But once that work has been done, it does need to be repeated, and SMA can be repeated in future years at minimal cost.
Great. Thank you, Kevin. And I will just jump in for the last section, which I'm going to go through quite quickly so that we can have ample time for questions for our primary presenters. The last part of our assessment, as I mentioned in the beginning, was a hydrological model for a watershed adjacent to the Fort Pierre area. We used SWOT to do this analysis. We did 3 scenarios, one with just the cropland data layer, so the single grassland class, another scenario with a grassland class defined based on the spectral mixing analysis, so we'll call this the enhanced or improved grassland class from, say, barren ground, sparse to very lush grassland. And then in a third scenario, we took scenario 2 and planted switchgrass on a few select areas that we thought might be degraded. Quote, degraded, or what we are calling kind of sparse to barren based on the spectral mixing analysis results. So that is the second class. That's scenario 2 that you see to your map, the map on the right is the reclassification. All croplands remain the same, and 5 classes for land cover grasslands. And then we converted it to switchgrass. The SWOT model performed decent compared to a gauging station at the bottom of Cedar Creek. There were little differences in flow between the 3 scenarios. However, in contrast to flow, there was very significant changes in sediment. Between scenario 1 and scenario 2, there was a 94% increase in sediment load, mostly due to the classification of more exposed ground, bare soil, which did appear to be true based on high-resolution Google imagery. Then between scenario 2 and 3, if we assume that the spectral mixing is more accurate, the planting of switchgrass did have the potential impact to reduce sediment loads. This chart right here shows the sediment loads and the variance between each of these classes. In scenario 1, the cropland data layer had an average of 12 tons. The grassland class had an average of 12 tons per hectare, and you can see the variance there. In scenario 2, of course, we had 5 classes and the larger and much larger variance within those classes. Grassland class 5 was near barren ground, and often these pieces of barren ground were on exposed bluffs or ridges, and therefore sediment loss was quite high. In contrast, in scenario 3, when you planted switchgrass on those areas, you had a much reduced sediment load for the comparable grassland that would have been there otherwise. Remember, this is all just modeling and SWOT, so we were not able to validate these results. However, the results do indicate that by classifying the grassland layer more accurately, there are significant implications to that, and therefore it suggests that further research needs to go into whether that's a more accurate classification. So I'm going to just whip through conclusions because we've pretty much talked about them all. We feel that the cropland data layer is a quote, good product that can be used to assess change. However, the accuracies should be addressed, and the assumptions, of course, always need to be stated. The cropland data layer can be enhanced for classification for different grassland conditions using spectral mixing analysis. Seems to be a very promising technique, as we talked about. However, robust upfront investment for field sampling and developing spectral signatures must be done for sites. And last, SWOT model does show changes in sediment and different water quality metrics based on changes in grassland condition. Those results need to be further tested and validated. Thank you very much, and I will pass it on to questions. And to Jess, I think.
Yes, thank you very much. Thanks to both of you. I think we've had quite a few questions that have come up. One in particular has that I'd like to go to first is addressed to Chris Wright. So if it's possible for Chris to be available on the mic. A follow-up on the question of the National Land Cover data set. When you state it's difficult to crosswalk the National Land Cover data set with the CDL because a certain National Land Cover class combines alfalfa and grassland, are you referring to the pasture hay class in the National Land Cover data set?
Yes.
Perfect. that was a quick question. I hope that answers a suitable answer for you, Rob. There's another few questions before we get into a wider discussion. There's a couple of questions from other panelists that have raised broader questions. So from Michael O'Hare, if it were shown that remote sensing is not good enough for policy making in this context, what action by whom would be implied? Use, say, astrology or guesswork for policy, or have no policy? I think I'll direct that question first, if I may, to Chris and then to Nagendra. Please keep your responses as brief as possible. We are running short of time. Thank you.
I guess I don't really understand the point of the question.
Okay, let me see if I can and help you there.
Okay.
So if it was shown remote sensing is not good enough for policy making, what should we do? Are we going to if the tools aren't good enough, as some are saying, then should we not use them? Or should we do something about it, like improve the cropland data layer, for example?
Well, absolutely, I would want to improve the cropland data layer. I mean, I think we need a national effort to improve grassland mapping by remote sensing. And, you know, because it seems like grasslands fall into this netherland between the NLCD and the CDL, because the CDL doesn't do, you know, it wasn't set up to do grasslands, but the NLCD especially merges types that we really don't want to be merged in terms of grasses and alfalfa. So I think, yeah, the solution would be a better data set. But I mean, I guess I would argue that the data that we have can be used. I mean, I don't see, I mean, I think we made some really logical adjustments to make it usable.
Okay, can I just stop you there? Michael O'Hare's responded and said, agreed with you. He says if there's no better tool, tools are ipso facto good enough to use until they're improved, right? So he's agreeing with you. May I just move to Nagendra? Nagendra, is there any kind of additional comment or clarifications on that particular issue?
Yeah, well, first of all, we can, I'm not saying we cannot use remote sensing. Remote sensing can be used to monitor grassland. What I said is that the cropland data layer is probably not the best data layer to do that. And again, I go back to my my definition that when we see grassland, I think most of us are just assuming that grassland which grows naturally. So if there's grassland which has been cultivated, which has been extensively managed, and if that grassland is being replaced by cropland, that's not a real environmental change. So I think if there's somebody from the serial layer, serial team in this webinar, he'll probably tell us that the focus of the cropland data layer is to map crops, and it does a great job of doing that. For whatever reason, it has not been mapping grassland. And so when we say grassland and club everything into one big broad category, that makes absolutely no sense at all. You know, I overseed my lawn. I probably irrigated more than it's required. I use more pesticides, and that is grassland. So, you know, so is that more environmental friendly than a cornfield? Probably not. Just because I call it grassland, we should not have that feeling that, oh, that's better than cultivated crop. So I think first we need to differentiate between the different type of grassland, and then we come to the question what's been converted, and then whether that's environmentally good or bad. So I think by just putting everything into one broad class and calling it grassland and making it sound environmentally sustainable or environmentally friendly is not logical.
Okay, we've got several more questions that I do want to get to the end of.
Can
So,
I reply to that first?
oh, sorry, sure. Briefly, if you don't mind.
The ecosystem services, so in our part of the world, associated with a grass hayfield versus a grass pasture versus a native prairie are not all that different. So I guess I would just disagree with you that they are substantially different, at least in our part of the world.
Okay, may I make a suggestion? I think if we are going to be circulating the slides, and in fact the webinar has been recorded, so participants will have a chance to see all these slides and listen again, and I think it would be helpful if my colleagues and I also circulate some of the work that's been presented here, for example your report and the various publicly available comments on either side. I think that would be helpful. There are a couple of other questions that I'd like to get to the end of. We only have 3 minutes left. So first of all, we do have 2 of the Cropland data layer team on the webinar. One of the questions they've asked is if the team were to develop a grassland data layer, what categories would presenters like to see? Now, I think that's too detailed a question to go into in this call, but I think it's a very important question that we'd like to follow up with our presenters after this webinar, and perhaps in the summary that we circulate to all groups, we'll try and include that. And so it's a great question. The second question from the team, are there any efforts to examine the newest CDL products for pasture accuracy as we continually try to improve the product? And number 2, NAS welcomes methods to improve CDL grasslands, and so would be interested in follow-up discussion. So I think if you, any of the presenters wouldn't mind answering that first question, are there any efforts to examine CDL products for pasture accuracy?
We haven't done that.
Okay. Well, Rick, who asks the question, I think we'll have a bit of a discussion with some of our other presenters and colleagues, and we'll also include that in the summary webinar output. So we have quite a number of questions all coming through right at the last moment. And I don't know if we're going to be thrown off this webinar or webcast at the time that stated, but I think it's worth going to a couple of these questions because they really focus back to the question about grasslands and bioenergy, and several of these questions are focused on the causal link. Are we sure that we can establish causal links between grassland conversions and bioenergy? And I think it's safe to say that certainly the work that we've seen so far is very difficult to establish that causal link. And I think what I'll do is hand over to Chris, Nagendra, and/or Mike and Kevin, who can just say a little bit more about that causal link and how it should be addressed.
Well, I'll just say, speaking from my part of the world, that farmers are responding to the sustained high crop prices, and I don't think it would be reasonable to say that those crop prices have nothing to do with the biofuels. So, I mean, I can't say, I can't quantify that, but I think it's fair to say that it's biofuel.
Okay, if none of the presenters. Oh, Nagendra, sorry.
Yeah, I just want to make one thing clear. I'm not for one saying there's no land use change due to biofuel. If we are going to produce biofuel at this scale, there has to be land use change. So that's a separate debate. What I was trying, my point was here that the methods we are using, the estimates we have, they have very high uncertainty in them. And we have to come up with, it might be the land use change is more than what we are predicting. It might be that it's less than what we are predicting. So what I believe is that we don't have the resources or the tools and the data to do this accurately, and we have to come up with a solution. Whether the guys who are doing CDL, they are going to do something about it, I don't know that. Or somebody else is going to take up this challenge and say, hey, I'm going to map all the grassland in the world or in a particular state or in the United States of America. But as of right now, all I can say that we don't have the tools and resources to do this accurately. There's a huge uncertainty that could be positive or negative. I don't know at this stage, but we have to do something about the data sets if we have to do this accurately.
I think that's a great place, Nagendra, on which to finish. We have come to the end of the webinar session. There are just a couple of notes that I'd like to make. Several of the participants have set questions that haven't been answered, and we will write to you individually to be able to feed back to you. But there's a couple of points, a couple of participants have sent information on existing projects and programs related to mapping grasslands, and we will include all the information that you send to us either now or please following the webinar. You please feel free to contact us. We'd like to follow up this discussion, and we will keep you informed of any further follow-ups that happen following this webinar. One of the participants indeed has mentioned a kind of overarching conclusion, I guess, which is that the distinction of intensity of use of natural grasslands remains a challenge to map accurately, and I think that's really one of the challenges Nagendra raised at the very beginning. We've got to start at the beginning, which is, can we start to map more accurately? One of the key takeaways that I had from this webinar was perhaps we need to start by thinking about what our objectives are, what are we actually interested in. Maybe we can start to map threat categories as opposed to trying to define every single grassland category going. But that leads us to the other conclusion that in fact, whilst there are probably lots of interested parties other than the bioenergy groups who are interested in grassland mapping, maybe the approach that the bioenergy folks thinks appropriate for improving grassland layers isn't the same approach as that group, wildlife conservation groups, may think is appropriate. So I think one of our presenters had already said this is a national effort. It's something that has to be coordinated, perhaps interagency coordinated, and I think that that's something that we'd like to follow up with in the follow-up paper, and I would encourage any and all participants, if you have further thoughts or clarifications or bits of information that you'd like to send us for that follow-up document, we'd very much like to hear from you. So all it remains for me to say is thank you very much indeed to our presenters for an incredibly thought-provoking and interesting set of presentations, and thank you very much indeed to all of you panelists for participating, sending your questions. We very much hope to be able to keep up with you on this in the future.